So looking through the test, you might see slightly different numbers here, but the concepts are the same. Very quick rundown. I don't know where that just went. All right. So the potato chip problem. What's probably the mean weight of a bag is below 10 ounces? What we're going to have to do, this is not a confidence interval problem, so we need to figure out the probability that X bar is below 10 ounces. This is a mean problem, so the conditions, very simple. If you got a simple random sample, we're going to have to assume the other n is not big enough, but we are from a normal distribution. That is given. All right, so we're going to find this probability. In order to do that, we need a quick z-score. The z-score here, 10 minus the predicted value of 10.2 over 0.12 divided by the square root of sample size. You have to do that here because we are sampling. This is because we are sampling. We have to use a sampling distribution. All right, because of that, we have to use that. All right, so quick calculation would give us negative 1.88, which allows us to very quickly go to the curve. Should be at 10.2. So 10 is almost 2 standard deviations below. We'll label the curve quickly. And then, so the probability that X bar is less than 10, we go to normal CDF, we can type that in. And that probability is about 0.03. So the sentence, the probability that a 24 case has a mean weight below 10 ounces is 0.03. Now part B is just using that information. We'll make a comment. So here the evidence suggests that 10.2 ounces is incorrect because the probability we got a mean weight of 10 or below, assuming we were supposed to get the 10.2 ounces, was so low. How low? 0.03. There's number one. Number two, it is believed 4% of these children have juvenile diabetes. Researcher did this. This is a proportion problem. So now we're doing the probability that a proportion, well, what is my p hat? The p hat here is 55 out of 1,700, which quick calculation is 0.03. That's what's going to go into my statement. The fact that this p hat is below the expected value 0.04 means it's less than. If our p hat was bigger, if p hat was bigger than the 4%, then our probability statement would have been the probability that p hat was bigger than whatever we got. Right? It's always the probability we got our result or something more extreme. All right, quickly run through the conditions. SRS, that's given. We need to make sure there's more than 17,000 children, not children with diabetes, just children, because it's out of the children, how many of them have the diabetes. Then we need to do N times P, so 1,700 times, it's P, folks, 0.04. That's bigger than 10. When you do 1,700 times Q, 0.96 is greater than or equal to 10. All right, we use P here, not P hat. You only use P hat for confidence intervals. So we're going to go find that probability, a z-score. The observed value is 0.03. The predicted value is 0.04. And the standard deviation for a probability problem would be P times Q over N. All right. Reminder, standard deviation of a sampling distribution with proportions, that's PQ over N. That's what's going right there. So our z-score here is about negative 2.10. Let's get a probability associated with that. All right, we were supposed to get 0.04. 0.03 was just below 2 standard deviations, so it's not looking very likely. Let's go to that normal CDF, plug and chug, and we'd see that the probability that our p-hat was this low is 0.02. So how likely is it the researcher got these results? There is a 0.02 chance that these results were obtained. So we go down here to part B, and that's where they're going to ask us, comment on the thought that 4%. So here, evidence is suggesting because it's so far off, 4% is incorrect. And this is because there was only a 2% chance we got our results. Or the researcher, I'll say the researcher. Researcher got their results. All right, number 3. Now they've given us some data. We're going to ask to construct a 90% confidence interval for means. Here's the deal. Sigma is not given. So what we need to do is set up a one sample t interval. And as soon as you write the term t, you need to write degrees of freedom. Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which means there are 9 degrees of freedom. Write the formula, x bar plus or minus t star, and then s over the square root of n. Quick run through the conditions. SRS, that was given, and it's not a big sample, but it does say assume these are normally distributed, so they are normally distributed. So those are good. Now it's a matter, go to the calculator, put this data in, and run your 1-var stats. We'd realize that the x bar is 12.96, and we always use s, 1.35. The t star, go to your table. The t star for a 90-degree confidence interval and 9 degrees of freedom is 1.833. So plug those values in, 12.96 plus or minus 1.833. You get that from that table, and then 1.35 over the square root of 10. That's how many are in the sample. We'll let the calculator, we called it a one sample t interval for a reason. The calculator can do that work for us. And that interval is 12.18 to 13.74. So I am 90% confident. This is also important. Some of us are not quite sure how to write this. Write it this way, that the true average yards per catch for all receivers. We're making a claim about the population. So based on this sample, we're making a claim about all wide receivers is in the interval, is in the interval. Don't forget this sentence. That's a big part of it. 12.18 to 13.74. We gave context. We now see what the deal is there. Now, if we would like to create a 90% confidence interval that has that margin of error of 3 yards, this is just sample size. Sample size always uses, when you're finding sample size, always use z star, which is the bottom row of that table, every time. So with means, the margin of error is equal to z star. Here it's actually, sigma over the square root of n. We don't know sigma, so we're going to have to use s. Okay, go to the table. We realize the z star, is 2.576. My standard deviation, I don't know sigma, right? But we do know that s was 1.35, so we'll use that. 1.35 over square root of n. The margin of error that they're interested in is 3 yards. When you solve this, you're going to get a very small number. You're going to end up with the square root of n equals 1.16. On some of the versions of the test, you ended up with an n. So n is 1.35. Some of you guys ended up with an n that was below 1. The rules don't change. You still round up. You always round up. So actually on versions B, C, and D, you only needed to select one receiver. For test A, 2 receivers are needed. Right? Because again, on tests B, C, and D, you got an n of like 0.6 or 0.8 or 0.7. So round up. Here's the thing, 3 yards is a pretty big, plus or minus 3. That's a margin, that's a confidence interval 6 yards wide. Look back at this interval right here. There's only about 1.5 yards. So all of a sudden, 3 yards is not that accurate in the context of this problem. So you probably don't need to interview or survey a lot of people. All right, last problem. In a survey of 1,037 adults, 643 were concerned about getting the flu. Construct a 90% confidence interval for the population proportion. So this is a 1 proportion Z interval. Something to note. Proportions always use Z. There is no T interval for proportions. So quick check of the conditions. All right, since this is an interval, SRS, we'll assume that. We need to make sure that there are more than 370 adults in U.S. over 65. That's a fair statement. And then since this is a confidence interval problem, we're actually going to go ahead and use p hat here. So the p hat for us is p hat equals 643 over 1037. That's a p hat of 0.62. So both of these are in fact over 10. Good to go. Write the formula. P hat plus or minus Z star. P hat Q hat over N. Take the square root. Plug and chug, folks. 0.62. The Z star associated with 90%. Now you just go get the right Z star. 0.62 times 0.38 over 1037. Let the calculator do this work for you. 0.595, 0.645, excuse me. Make sure that I write that clearly. So I am 90% confident. If your interval is different, you just have a different Z star and your sentence is slightly different, but it's essentially the same thing, right? We're 90% confident. The true proportion of adults over 65 concerned with the flu is between 0.595 and 0.645. To do the sample size problem, again, here margin of error is equal to Z star times P hat Q hat over N. Plug and chug. Within 4%, that's 0.04, folks. Z star, just go get the appropriate Z star, plug in the appropriate values, and then solve this thing for N. Right? This is just algebra. The N here should be about 565.7. Always round up, so we need 566 people. Now, if you rounded slightly differently along the way, you might have gotten a slightly different number, but the concepts here remain the same. The concepts here from test to test should be the same. It's just we're using different Z stars and slightly different numbers.